Hello guys. So if you have seen my the last video I've uploaded. So uh, in this lecture, what I will talk about is basically the solutions, the solutions of means liquid, okay, liquid mixture, and those solutions are have a particular different properties. Let's say if you have a liquid, hmm, liquid. Now that liquid, think at particular temperature. Okay, let's say temperature T, you have a liquid. Okay, so you pour this liquid in a container. It's a closed container. Hmm? A closed container, and this is the liquid. Okay, and you have put at T, temperature T. Okay, now what will happen? In this case, the molecules, the liquid molecules, which are here, will have the intermolecular force from all the sides, right? Hmm? Just think the concept about surface tension. Hmm? And the molecule present at the surface, they will have a intermolecular force from the bulk side. Hmm? Now, in this case, at this particular temperature, the molecules will try to this escape from the surface. Okay. Now, when I would say this is a particular a moment of phase transition. Hmm? When a molecule from a liquid part, okay, liquid region is trying to escape to a empty region. Okay, I would say this is an empty region. So they form vapor phase. Okay, this is vapor phase. Okay, and this is my liquid phase. Okay, so there will be a this vapor, if the molecules present in that vapor phase, okay, will have a particular force, or I would say pressure. Okay, vapor means they are in the gaseous part. Think like that. They will this molecules will have a pressure on the liquid surface. Okay. Now pressure, this pressure exerted by the molecules present in the vapor state of the corresponding liquid is known as vapor pressure. Acha, you can write VAPOR or VAPOUR. Any of them is correct. Hmm. Vapor pressure. But whatever you write, follow anyone. No, don't mix. Okay. So this is what vapor pressure is. Now the molecule, hmm, the molecules at the liquid. Let's say this is liquid. Okay, this is liquid, and the molecules here, they have a tendency to escape from the liquid to the empty vapor region. I will name this region as vapor region. Vapor region. So the molecule will have a so this phenomenon of the molecule is called the escaping tendency. The escaping tendency. Okay, the escaping tendency, and this escaping tendency is basically the more the escaping tendency. Okay, the more the escaping tendency, the number of molecules in the vapor phase will be more, right? more the escaping tendency, number of molecules of liquid in vapor will be more, right? If this is more, then what will happen? More vapor pressure, more vapor pressure, right? That means the vapor pressure is proportional with the escaping tendency. Hmm? Okay. Now, which of the liquids will have uh, which liquids will exhibit vapor pressure? That's a big question. Let's say if you have if you have a liquid, hmm, if you have a liquid which is at room temperature, which tries to attain more in vapor phase, more vapor compared to compared to it would like to stay in the liquid phase, um like any spirit, rectified spirit or methylated spirit, alcohol. So they will have a high tendency at room temperature to vaporize. Okay, this process is known as evaporation. Evaporation, and those liquids which which evaporate at room temperature is known as volatile substance. Volatile substance. Hmm. And those who does not evaporate are called involatile substance. Involatile substance. Now, if you have so uh, now if you have, let's say, a mixture of volatile substances solution, mixture of or a solution of volatile substances, then what you will say? Then the vapor pressure, the vapor pressure more will be exerted by the more volatile substance. Keep that in mind. Hmm. So point is here, mixture of volatile substance, okay, vapor pressure, vapor pressure will be more of high volatile substance. Here means if you have, let's say, A and B, okay, solution of A and B, and if A is more volatile compared to B, then in vapor phase you will have more A compared to B. Hmm. So if you have more A, then the vapor pressure of A will be higher compared to B. Hmm. Okay, so these all things happen at a particular temperature. Mind it. Keep that in mind always. Hmm. Okay. Now, when this the first time this prop thing was introduced, hmm, the vapor pressure, the liquid vapor equilibrium. Okay, when one person from in one chemist actually, he thought that okay, if I take that, so then he thought that okay, what will be the composition? Since we are talking about the solution, then definitely it is based on some concentrations also. Then he thought that okay, what will be the composition of that solution such that such that we will try to figure it out that what how the substance will behave they are mixed together, what will be the vapor pressure, and how the composition is dependent. Hmm. So that person is Raoult. So he gave a law. So it's very simple. Very simple. What he said, okay, what he said, as I said earlier, is that if you have the more number of substance in vapor phase or a liquid phase, the vapor pressure will be high. That's what he said. He said that the vapor pressure, if you have, okay, if you have a solution, if you have a solution of two volatile substances, solution of two volatile substances, okay, let's say one substance is substance 1 and another is substance number 2, okay. Acha. Now this substance, hmm, this substance, let's say, has liquid. In liquid it has mole fraction x1 and mole fraction x2, hmm, okay, and vapor pressure it has P1 and it has vapor pressure P2. Clear? Hmm? Okay. Now T, it is vapor pressure. Hmm? Okay. Now what he said, that this P1 will be proportional to x1. That's what he said. Hmm? P1 will be proportional to P1 and P2 will be proportional to x2. Likewise. Hmm? Okay. Now what I have to do, I have to remove this constant, remove this proportionality and put a constant here. I am putting, let's say, P1 is equal to some constant K into x1, right? Okay. So, or K is basically P1 by x1. Okay. Now, since the mole fraction is x1 and x2, so hence we can write x1 plus x2 will be equal to 1, right? Acha. Now think, okay? Think. This is very interesting, important here. When x1 is equal to 1, x1 is equal to 1, then my x2 is equal to 0, correct? Okay. Now, what is x1 equal to 1 suggest? This suggests it is a pure substance, not a mixture. Pure substance, 1, 1, pure substance of the component 1, okay? Pure substance of the component 1. And in that case, what I will have here, K is equal to P1. Now, this is the vapor pressure given by the substance at its pure form. So, I will write this K is P1 0, or you can see in many cases it can be write as P1 star also. Okay, so I will write his P1 0. Clear? Okay, so if I put here, then P1 is basically P10 into X1. Okay. So what is P10? P10 is basically the vapor pressure of the substance 1 of the component 1 at its pure form. Hmm? Okay. So P1 is basically the vapor pressure of component 1 at its pure form. Clear? Okay. Okay. Now let's say, so similarly, when I can write, similarly I can write P2 is equal to P20 into X2. I can write this. Hmm? Okay. So this is so P20 is basically vapor pressure of C2 at its pure form. Clear? So P2 is equal to P20 into X2. I can write. Okay. Now see here. If I see the total pressure. What is total pressure? P1 plus P2, right? P1 plus P2. So let's, and that is equal to nothing but capital P, which is total pressure given by the A. So what I can write here? Okay. So I'm just putting this property here. So P1 is equal to P10 x1 and P2 is equal to partial pressure is P20 into x2. Okay, I'm just wrapping out this part. Just be with me. So what I have here? So P total is equal to what? P1 plus P2. So equal to where can we can just replacing this to here. So P10 x1 plus P20 x2. Okay. Hmm. Okay. What is x1? X1 plus x2 equals to 1. So I can write instead of x1, I can write P10 is 1 minus x2. I can write, right? Plus P20 x2. Okay, so if I do some calculations here, algebraic, P10 minus P10 x2 plus P20 x2, or I can write here if I take this P10 uh, minus common, so P10 minus P20 into x2. I can write this. Hmm. If I take the so if this is okay, if I take plus here, so P20 minus P10. Okay, now it's clear. Okay, now so what is this is the expression of total pressure. Hmm? Total pressure means if I know the mole fraction of the one substance, then I will easily able to know the mole fraction. Sorry, the total pressure and the partial pressure. So using the partial pressure, we can easily calculate. Okay. Now, if I plot, it's a very important graph. So you just need to be with me very carefully here. Okay, if I plot, let's say, since okay, so see the expression is here. What expression is my P total? P total is equal to P10 plus P2 minus P1 into x2. It is y is equal to mx plus c type, right? Mx plus c type. Hmm? Okay. So if I plot in x with respect to x2, x2 means this is can be 0 or this can be 1. Okay. I'm plotting the vapor pressure here. Vapor pressure here. Okay. And why I put this axis? Later. I'll tell you later. Okay. Now just don't try to mug it up. Just clearly, just logically think. This part. Just put. I will just put the value. Nothing. X2 is 0, this axis. If I put x2 is equal to 0 here, so this part is 0, so your P total will be equal to P1 star. Let's say my P1 star is here. Okay. Achha. Now, initially, let's say I'm assuming that the component 2 is more volatile compared to component 1. So, the vapor pressure P2 will be higher compared to P1, and and P2 star, the sorry, 0 will be greater than also P10. Okay. Now this is okay. Okay. Now when your x2, if x2 is equal to 1, x2 is equal to 1, if I put 1, then P1 cancels out. So P2 will be there. So P2 will be here. P2 0. Clear? Now P1, P2. Okay. Now what will happen? This equation is basically a linear axis. Okay. So this is a linear plot. Okay. So I will draw this one. Acha. Now if I increase the x2, what will happen to P1? If I increase this x2 value, the P1 value will decrease, because the more you increase the other component, the one component, the other component concentration decreases, right? And the vapor pressure is decreases, because vapor pressure is proportional to the proportional to the yeah, mole fraction. So this the P1 decay will be this. Okay. Similarly, at 0, your this highest is P1 and x2 is equal to 1, it is P2. So clear. But effectively, if my graph is increasing from this one. So from P1 to P2, this is the change in the graph. Okay. So this is basically your partial pressure P2, which is increasing. This is basically partial pressure P1, and this is basically your P total, which is equal to P1 plus P2. Okay. This graph is called a phase diagram. Phase diagram. Okay. This graph is called a phase diagram. So at this part, if I think, let's say, so a phase diagram at particular temperature T, particular temperature T. Hmm? Okay. Now, if I rub this part, let's say, now, what I have here now, what I have, hmm, if, let's say, Y1, if Y1 is the mole fraction, Y1 is the of mole fraction or in vapor phase. Mole fraction of component 1 in vapor phase is Y1, and mole fraction of component 2 in vapor phase is Y2. Okay. Then what you can write here, according to the Dalton's partial pressure law. So according to Dalton's partial pressure law, okay, we can write now P1, which is equal to Y1 into P total, right? And P2 equal to Y2 into P total. This we can write, right? Okay. Hmm? So for any component, we can hold this relationship. Okay. So this is till now, this is the Raoult's law and the application of the Dalton's partial pressure law in the vapor phase. Okay. So what we have learned so far is that the Raoult's law is applicable for the volatile, well, not all the substances, but when you have a volatile substance, then what you have? then you have a vapor pressure there. Hmm? And that vapor pressure is basically proportional to your nothing but the mole fraction of the mole fraction in the liquid phase. Because the more the volatile substance will be there, the more it will go to the more will it have a escaping tendency, and it will have a more partial vapor pressure. Hmm. So this is the curve we obtained from the using the Raoult's law and the mole fraction concept and the partial pressure law. Okay, so next I will talk about is the details about this Raoult's law few parts. Okay, and then we will directly go to the concept of the ideal and the non-ideal solutions. Okay, and from there we will show some anomaly in case of this Raoult's law. Okay, and then finally we will end up with the discussion of the azure.